works. Nice. So, good evening, everyone, and we are glad to see you, our participants from summer school and participants outside. So, we have our traditional coffee and data science talks, and tonight actually, and tomorrow, we will have two talks that will be presented by our lecturers, actually lecturers of our summer school, and from Estonia, from Tartu University. And tonight I'm really glad to present you, to introduce you, Dima Fishman, Dmitro Fishman, from Tartu University, originally Ukrainian. Right, so Dima he graduated his master degree in Tartu, and right now he is a PhD student in Tartu, right? So also he do a lot of research in bioinformatics. I think that Dima may tell you a little bit more about himself. So please welcome Dmitro.
Thank you very much. I hope you hear me well, even if you sit somewhere there far, far away, thinking that might be something interesting will anyway pop up from this kind of lecture. Thank you very much, Alexei, for your introduction. He knows what kind of parts of the speech I spend most of my time in, so he decided to cut it up. Yeah, I'm actually from Tartu University. We, with Elena Sukis, represent here people that do some kind of computer science for biologists, for medical studies. So on behalf of these people from medical studies, I wanted to deliver this lecture about brain and deep learning, not just deep learning, but let's do and think about somehow biological structure, which it was inspired by, and this is obviously a brain. So today I thought you will be talking about brain, a little bit about brain. So what do we know about brain, how it works, and some of the things, some of the facts that we definitely sure about the brain. Then we would go into deep learning. So some of the basic concepts of deep learning, how it works, what is the structure of deep learning algorithms. And then we would go back to brain and see what actually deep learning can teach us about the brain, about how our brain works. Can we make a more serious kind of parallelization between brain and deep learning and say that they are very similar, or can we say that they're completely different and there is nothing common, there is nothing that we can say that it's acting the same way. So let's see what this lecture will bring. But I also wanted to mention before I start that this lecture is based mostly on Raul Vincente lecture that he delivered at the University of Tartu in April for the right to teach in the University of Tartu. So let's start. Before we go into details about the brain, there is nothing I can add to what you already know probably about how deep learning is learning is popular. So there were, I don't know, literally hundreds of different newspapers publishing really loud headlines like deep learning is going to change the world, or there is some kind of lesson that neuroscientists can learn and inspired by human brain. But there were even more interesting headlines like deep learning and machine intelligence will eat the world, or androids do dream of sheep, or some kind of even more profound kind of interesting stories that you could read from articles. Not knowing what actually is deep learning, you would make probably some interesting conclusions and probably get scared. But mostly, this is a huge hype nowadays, and I would explain why it's a huge hype. So one of the reasons why it's so popular is that it empowers us to tackle problems that were considered to be unsolvable or near impossible to solve. One of the examples is almost near time speech recognition and translation to the other language. So this is an image of a beta version of Skype that promises you that it would translate whatever you say in Russian or in Ukrainian to Spanish or Chinese at the same time. So that was a beta version back then in April, but I'm not sure if I think they haven't made it into even alpha version. So, but I think it's a pretty cool example, because if you think a little bit about this problem, you will come up with a sequence of complex problems that you should solve in order to be able to do this kind of thing. So first of all, you have to record your voice. Then you have to translate whatever you say in your local language to the so you have to learn the representation of what you have said in your language to machine readable form. So you have to read it and understand what's the representation. And then you have to come up with a way to translate this kind of representation into the other language, into the language of your preference, of your choice. And obviously then you have to synthesize this thing. So what actually deep learning has allowed us to build some kind of one end to the other end solution, which is absolutely awesome, and that's why people all over the world are so fond of this technology nowadays. The other application which is very, very popular, and Alexander Baev here is a representative of this field, is the computer vision. Obviously, it has blown up all the previous records in the computer vision. So for example, if we talk about self-driving cars, Google self-driving cars, they have 2 cameras at the top of the car, and what they essentially do, they try to map this kind of images that they receive from the car, from the top of the car, and try to classify each of the parts of the image into some of the classes like buildings, crosswalk, pedestrians, roads, and stuff like that. So they have to be really quick because, well, you're driving, right? And the other thing is they have to be really, really accurate to make right decisions at the right moments. You also should remember that computers do not see like we do. Normally, as we drive, right, there is no problem in saying that this is a pedestrian or this is a tree, right? But what actually computers see is the tree matrix of values from 0 to 255, and they have to really quickly say which bunch of this value is a tree and which is a pedestrian and which is a small kid just running next to your car for a falling ball or something like that. You should be really, really fast here. Yeah, and I think this is very, very famous. So DeepMind has came up with an algorithm that is called AlphaCo that has, first they have beaten the European champion 5-0. The match was 5-0, they won. And then they have decided to try their best, and they fought with the world champion of a game called Go. This game is a little bit different from chess or poker or even Monopoly that computer algorithms has beaten before, because it has a grade 90 by 90, so it's pretty wide and pretty. So the number of possible choices is pretty large. If you multiply 90 by 90, it's larger than in chess or in other games. So it means that it's a little bit harder to brute force the algorithm, to brute force the game. You can't just simply run all possible solutions and find the best one and just be happy with that. You have to be quite smarter and faster. So so they beat this world champion 4-1, which was an amazing result for the world champion, obviously, because he managed to beat at least once. Comparing to the European champion, it was infinite time better. And the point here was that there was a boxing ring, and there were 2 corners, and one corner was, so one fighter was actually a biological system, and the other corner was occupied by the artificial system. So the idea of this talk is what kind of things we can learn, these guys can learn one from the other. And well, in some of the applications, in some of the fields, as you can see, this guy is actually kind of more skillful, and he actually runs and rocks. So yeah, we will start with a crash course on brain. Then we'll go into deep learning, and then we'll go into a famous dictum about what you can't build, you don't understand. So we can't build brain yet, but we are kind of on the way. So what do we don't understand about the brain? So let's start with a crash course on brain. This is not a brain. Obviously, this is not a brain. But this is a sea animal. It's called sea skirt, which can teach us some important lessons about why do we have brains on the first place? So what is the purpose of the brain? So what is interesting about this animal is that it, at some point of its life cycle, it travels around the sea and then it attaches to some reef. And from this point onwards, it gets paralyzed and doesn't move anymore at all. It just stays there and it catches some nutrition through this open mouth here. It's a mouse kind of thing. And this is basically no walkings, no fresh air thing, nothing, just there. And what is interesting is that after it paralyzes, after it attaches to the reef, it internalizes its own nervous system. So it literally eats its own brain. There is no need for it anymore. So some people might get a little bit disappointed thinking that we need brain for some thoughts of existential risks or existential problems. Why do we exist on Earth or something like that? But that's not true. We actually need brain to move, and that's the main purpose of the brain, according to this kind of as we can illustrate. So the brain is nothing more than just 1.5 kilo of some kind of mass, a spongy mass, and it is a CEO and data scientist of your body. So why it is a CEO is that because it takes decisions. It is responsible for decision making. This is the only guy in your organism that makes decisions. And the other thing is why it is a data scientist is that because it has to collect all the sensory information that comes from the outside of the world, and then basically organize the sensory information, store it, and make sense of it. So that's the purpose. That's the main kind of function of the brain. So the thing is, it's quite complex. It's quite complex and it's quite a mess. I will talk about why and a little bit about the structure, but it's really complicated. And the thing is, there are many things that might go wrong with the brain. And if they do, usually because unreversible changes in the behavior and in the basically lifestyle of people that this basically happens to. So one of the examples is Alzheimer's disease, which Yelena has started a project about. It's really far from being curable disease, and there is a good reason for this. So one of the reasons is that brain is nothing more than just a lump of porridge. It's a huge mess. You can't understand just by looking at it what's the function that it runs, what's the algorithm that is going inside, what is the iteration of the algorithm, what is the loss function. You can't just can't make sense of it if you just look at it. And this is Richard Gregory, very famous neuroscientist who was actually cited this quoted from this slide. But obviously, something we know about the brain. So there were hundreds of years of research, and well, definitely we kind of have some info about the brain. So there were studies on micro level, and there is a gross anatomy of the brain. So what is connected to what inside of this organ? So if I would cut somebody's brain like that, we would see this kind of picture. So we are interested in this picture here. And in particular, we are interested in the small region that is called thalamus, number 12. And this thalamus is actually, the thalamus is 7, is actually a collection of, this is a center where all the sensory information first comes. So this is a place, this is a gateway of the brain for the sensory information. There is one type of information that is called smelling. You don't get it into thalamus, it finds its own way to the brain. It has some specific pathways. But in principle, all the other sensory information, like, I don't know, some auditory system, visual information, and so on, it all comes into the thalamus first. And then if it's visual, then it goes to visual cortex here. If it is auditory system, it goes to the temporal cortex, and so on and so forth. But the main thing here is that the first gateway is this thalamus, number 7. yes, if somebody touches you, then probably the sensory information will go here. And so we actually will be talking now a little bit about this cerebral cortex. So this is an upper level of the brain here. And why it is important, why it is interesting to neuroscientists, and why this might be interesting to people that do deep learning, is that it has this, well, it consists of about 6 layers, and it's quite actually thin, and it covers the brain like that. And you can see, well, kind of familiar structure. So if you print out some of the AlexNet or some kind of larger networks like VGG, you would see, well, it doesn't look completely exactly like this, but it has some kind of style. And what actually we believe that this structure, this cerebral cortex, is the most important player in such functions as memory and attention and language. So these are the high cognitive functions that we humans carry out, and that's thanks to this cerebral cortex. And obviously these small dots are neurons. So let's talk about neurons, and there are actually 2 main types of the cells within the brain. One is called neuron, and the other one is called a glial cell. So these glial cells were for many years believed and considered to be a supportive function of the neuron. So they're basically a supportive personnel. They don't really care much of the most responsible roles in the brain. But recent reports that actually I came across were suggesting that glial cells actually do carry some important functions and could be influencing brain in ways that we have never even imagined. But this is talk about neuron and deep learning, so we'll be talking about neurons. There are about 100 billion neurons in the brain, and basically every neuroscientist would agree that these are the main computational units in our system. They are responsible for processing, signaling, and storing elements, and so this is basically the main function of the neuron. So the structure is the following: you have dendrites, you have a cell body, soma, and then you have this output level, which is axon. So the thing is that it listens to other neurons by dendrites, then the signal goes to soma. Something happens within soma, it basically accumulates, and then it propagates the signal forward through the axon. So this is how one computational unit mostly works. Neurons as computational units, as compared to computers, are very unreliable. They are very slow, so they are not firing. They are not actually in a hurry to fire the signal forward. So it's about like a kilohertz of the frequency. They are very unreliable. So in 50% of the cases, when one neuron fires a signal to the other neuron, this signal is not listened by the other neuron. So half of the communication is completely lost in our brain. And that's why some people say that we are not using capacity of our brain for 100% or something like that. That's what I've heard. But I mean, this is actually for a good reason. We'll be talking about this good reason. So it's not just we are so stupid we're not using half of the communication. It's just because it's actually important that we are not listening for half of the communication. Also, we're actually losing about 50 to 80,000 neurons per day. The thing is that if we're talking about Alzheimer's, then it's 10 times more neurons. We're losing like about 500,000 neurons per day. And that's why we actually, basically patients lose their memories, lose their cognitive abilities and things like that. That's why it happens. So other thing which is important is that neurons are capable of reorganization. So they know how to reorganize their connectivities. So they might connect at one point to one neuron, but then they might reconnect to some other neuron. And that is basically that is believed to be the main reason why we are capable of memorizing things, why we are capable of speaking and having and keeping attention and things like that. So this is the main reason. Yeah, as I said, actually, if we compare brain to the computer system, in the computer we have CPU is the main place where information is pre-processed and processed in principle. Then we have memory cards like RAM, where we store information. And then we have some kind of communication buses that transmit this information or send this information through in the computer. If we talk about the brain, then this is not the case. This is not working. The way it works is that neurons are all together at the same place. So they are both, so they're actually storing, transmitting, and they are also manipulating information. So they are also processing information. So this is all happens in the same place. That's the difference. That's the difference between computers and brains. So how do we make sense of the world? There is a small illusion. There will be a small illusion here. And I would like you to participate as well. So tell me, which of the small dots here, they are popping out or popping in? Which of them popping in or which of them popping out? Think about this a little bit. Hopefully you see that this guy here is popping in, right?
Yeah.
So it's actually this way. So you kind of press that.
You can't say it.
Sorry?
You can't say it on this picture.
Yeah, you can't say it, but hopefully your brain says that this guy is popping in. If it's not the case, otherwise, please guys go and talk to Elena. Probably will take your blood for some other analysis. But so hopefully everyone has to see that this guy is popping in. But what happens if I would revert the image? If I would just kind of put it upside down? Your answers would change probably. It would reverse. So now this guy's popping out and the others are popping in. So why this happens? This was the same guy, so the same image. It was just reversed, and now we see a completely different picture. There is one thing that is called Bayesian rule. How many of you know Bayesian rule? Yay! I'm actually in deep computer science summer school, so people should know about Bayesian rule. But let's see how Bayesian rule will help us to understand why this phenomenon is in there. So Bayesian rule is very simple. It's like this kind of formula that calculates the posterior probability based on likelihood and what is there in the world. So basically, what we are interested in is how likely something to happen based on what we see or what we feel. This is what we are trying to calculate every time. This is what actually our brain does very, very well. Then you have this, the likelihood. What is the probability of what we see given what we know about the world? So what is the probability of what kind of stuff might come to our sensors, given that we know that the world is basically, this is how the world is. We have some, we have some experience about the world. And that's what the world is, the probability of this being in the world. So now let's try to compare these two probabilities together and see which one is bigger, which one is larger, and which one has more chance to come to our brain. So first of all, we would apply a Bayesian rule. So we have a posterior, likelihood, and then we have some prior. So prior is the way we think about the world, and then there is this likelihood which we talk about, and then the sensor given basically world given the sensor information. So what's the probability of this guy popping in given this image, right? So let's try to estimate this. First of all, we have a term, conditional probability of image given that this guy is popping in and the light shines from below. Then we have a probability of this guy just popping in, just popping in. And then we have a probability of light shining from below. So what we can actually say from this formula. So we can say that this thing is quite randomly likely. So it's fine. Some stuff in the world could be popped in, and some stuff can be popped out. It's fine. It's like 0.5. There is no more or less bias in the world that we have only stuff popping in or only stuff popping out. So we could actually assume that this is half. Then we have this probability of this image, seeing this image, given that this thing is popping in, and the light shines from below. So we see light shining from below, and this guy is popping in. It's one actually. It's quite fine. If you would assume that light definitely shines from below, and you kind of think that this is popping in, then it's fine to see this kind of picture. But let's just leave this one for a while, and let's just try to estimate the same what happens with the popping out. So the probability of popping out given this image is the probability of image given that it's popping out and light shines from above, which is this term and this term is the same, because it's absolutely fine in both of these cases. If light shines from above and this guy is popping out, to see this image. And it's absolutely fine to see the same image if it's popped in and light shines from below. It's absolutely okay. So we could just forget about these two guys here. As we just assume that probability of different stuff in the world popping in and popping out is almost the same, we could also throw out these two terms. Well, they are also equal, they are half. There is no bias in the world about stuff popping in or popping out. But, so these two guys are different. So our prior about stuff being, about light being shining from above or shining from below is different. Usually, normally, we see light actually shining from above, not from below. That's why our prior probability that light shines from above is much higher than light shines from below. And that's why our brain says that the probability of this thing popping out is much more likely than the other option. Do you see this? Right? So what brain does essentially, it decides for you what is in the image. So given your sensory information, it tells you what you see. You're actually tricked by your brain. Your brain guides you through the image. You get some sensory information, but the brain is the thing that tells you what do you see, actually. So that's the main kind of trick of the brain. It integrates your prior knowledge that you can have while you're experiencing your life, or with your genetics, just because your ancestors have experienced the same thing over and over again. They saw a sun above over and over again. And they just memorized, and this memory is the connectivity in their brain that they have passed to you through their genes. That's why seeing these kind of images, you see them popping out rather than popping in. So what is also important and interesting is that our brain has this hierarchical structure of things. So first we see stuff with our eyes, and then it goes to the brain, to the visual cortex, and has this multi-layer structure here. So you can actually also see the time, milliseconds, of the signal propagating from retina until the last layer. And brain is so good, efficient to tell you the answer in 100 milliseconds. It tells you what you see in 100 milliseconds, which is pretty efficient structure and well trained, million years to and many cores to train this kind of structure. So now a little bit about deep learning and machine learning principle. So we'll start with three main types of data that I would come up with as a time series data that you have each point of on some kind of value corresponding to the time point here. You would think about this as a sequence of numbers. Then you have pictures. Basically, pictures. These are these three matrices of RGB, red, green, and blue, which you see is the way, but this is how the machine works. This is how machine sees it, and it's also a vector of numbers. And then you have some textual information. You also have a vector of basically occurrences of words, and you can assign frequencies to each word, and then you have a vector of length of the vocabulary of your text. So these are different tasks of machine learning. There is a supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is pretty simple in a sense of task forming. You have images, you have labels of those images. You basically transform these images and labels into the feature space, so-called feature space. So they would transform into the vector of numbers. Then you have labels of those features of those those images, and then you're given a new image, and the question if it's what kind of label it corresponds to. Yeah. Then you have unsupervised learning, where you don't have any prior information about the data that you're dealing with, but you have to build some kind of model that would say there are a couple of groups in the data, so you should look up carefully more, and then you'll probably find out what is important about the data that you haven't known before. And then you have reinforcement learning. So you have some kind of policy for an agent to behave well, and then you reward the agent if he has done what it has been made for, and then you punish the agent if it's going outside of the boundaries. So what we will be focusing here is the supervised learning. What's the supervised learning and the shadow machine learning, as they call it, is focused on is to build some kind of a transformation of your points from the initial feature space to some kind of other feature space that would be basically would make it possible to distinguish between a few classes, let's say, between dogs and cats. So what is the function that would transform initial vectors of numbers that would represent these images into the higher dimensional feature space that would make it possible to easily split these images into two categories? So there are three options for this sigma function. One option is that you basically would pick up this phi function for each separate task manually, which means that you would incorporate some of the prior experience about, I don't know, image recognition or speech recognition or other domain from the expert that has been there for this domain for many years and knows that the distance between eyes is very important to distinguish between two people. So this is the feature you have to go for example. Then you have basically genetic functions. You try to map from high dimensional and try to generalize. You try to somehow come up with a function that would make it easier to distinguish between two classes given some kind of generalization. So you might use some kind of kernel machines in SVM and things like that. And then you have a learn option, which means how to acquire those features on the way, on the fly. Can you build a mechanism that will just simply look at the data and says you need to pick up this kind of feature in order to reproduce, to distinguish between two classes? And we actually are interested in deep learning as a third option that would learn those features automatically from the data itself. And that doesn't mean that we wouldn't be allowed to have both advantages of the first and the second approach as well. So we would incorporate the domain knowledge and try to build some kind of a mapping of the feature space into the other more capacity learning feature space. So what is deep learning is basically a way to it's an adaptive nonlinear preprocessing to model complex relationship among the data. So what you'd like to be is you would like to go from space 1 of images into space 2 of broad categories of like a horse, car, and so on and so forth. So that's the main goal of the deep learning. What are the non-linear preprocessing units that would make it easier to get it from space 1 into space 2? In practice, it's an artificial neural network with many different layers. That's what we call deep learning. Here is a small history recap on how it was developed and what's basically what's the path of deep learning to nowadays. So first of all, there was this first paper by McCulloch and Pitts we actually, many people would argue what was the first paper, because you could see in the Facebook or somewhere that new first papers would come up even like 18 or something century, and that would say I was the first one to publish some kind of stuff related to deep learning. But so that was believed what was the first paper published about kind of related to deep learning is the logical calculus of the ideas and immanent in neurons activity. And these guys, they tried to build a representation, or they would try to model the neuron so that as a computational unit that would be able to compute some kind of function. Actually a logical function. So that was the aim of the study. So how to model a neuron in a way of a computational unit that is capable of producing, capable of computing a logical function. So it has some weights on the input side. It has a sum, so they believe that you need to sum up different inputs. And then it has some linearity and some output, which was essentially connected to aggregating the signal forward. Then there was a Rosenblatt, it was not a paper, it's actually been implementation of the Perceptron. The Perceptron was a little bit more sophisticated, and that was the first implementation of this previous concept that these guys published. So that was a physical implementation. So they also had weights, they have nonlinearity, they have output, and they first tried to train the system so it would model the relationship between input and the output. So if you think that deep learning is in a high, basically is very popular nowadays, then you should read what New York Times has written there back then when Perceptron was implemented. They said that the Perceptron is the embryo of the electronic computer that is expected to be able to walk, talk, see, write, reproduce itself, and be conscious of its own existence. So you see that we might be very far from there. It seems because we have the same headlines now. So then there was this very famous book published, which actually tried to, given this perceptron, layer of perceptron, they tried to compute XOR function. And these guys actually proved that this is impossible. With a layer of perceptron units to compute a XOR function. Didn't work. But many people consider this to be a death of deep learning. So there was the first winter of deep learning algorithms after this book. Then there were a couple of papers published saying that actually training neural networks isn't hard, isn't impossible. You can't train neural networks with 3 nodes or something like that. There were a couple of attempts before these papers to publish an algorithm that would allow more efficient training of neural networks. But as you can see that this paper claims that it's not possible. They didn't succeed quite well at that time. But Hinton here is considered to be a father of deep learning, even now. But they have some kind of discussions and arguments about this. So basically, so we have talked a little bit about the deep learning, and it's a collection of simple trainable mathematical units which collaborate to compute a complicated function. It's supervised, well, basically it's compatible with supervised and unsupervised reinforcement learning. And it's loosely brain-inspired. So you saw that some things may be a little bit alike the brain structure, but we didn't see a complete correspondence. So this is an artificial neuron, which I actually showed you before. It has weights and dendrites. Actually, I showed you the biological neuron, and you can see that this one, besides this some more geometrically correct lines, it does look very similar. So you have a soma. This is a cell body. Then you have axon. Then you have dendrites and the other axons from other neurons. And this is something that scientists would come up with. They said that inside of this cell body there is this non-linearity. This is a sigmoid that is inside of this the cell. This is a network. This is how the neurons are connected to each other. You have input layer, you have output layer, and then you have a propagation of the signal. So they connected to each other in a way that they would compute signal based on the previous weights. So you have signal going from the input to the output. So this is a pseudocode of the algorithm. It's very simple. Pick a random training case, run neural network on input X, and modify connections to make predictions closer to Y. So basically here, you have some X here, you run it through the network, you have some output, which you have to make as close as possible to the ground truths that you know. This is a supervised approach in here. This was just recently published. You can play yourself. This is a sandbox example. You could build your own neural networks. You try to map. So there are data points here. There are two classes, spiral. You try to make a neural network that would predict this data perfectly. So the question is, can you do it perfectly? And by adding neurons, by training on with different hyperparameters and stuff like that, you actually see what is the loss at any given iteration and things like that. So you could actually try this. But now I actually wanted to go through one iteration of deep learning algorithm just to torture you. And so we now have a very small network. It consists of 3 layers. There is this input layer here, output layer here. So you have 2 neurons in each of the layers. And this is called bias term. A bias term, you just sum it up with other neuron inputs in the hidden layer. This is called hidden layer. That's why H stands for there. You have weights from each neuron to each other neuron. And information from here goes and propagates into the further layers. So let's try to compute this. So we have input on H1. So basically, what goes inside here? It's very simple. You have weight 1 here, 0.15. It multiplied by the input 1, 0.05. Then you sum up with weight 2. It's here, 0.2. Multiplied by I2, which is basically input 2. And then you sum up with the bias. Bias is 0.35. Somebody could actually, in your laptops, you could actually do it and tell me what's the solution. But essentially, it's 0.3775. So the signal here that came into the neuron is 0.3775, and this is the input here at this level, and it goes through this sigmoid function. So we have to apply the sigmoid function. This is what this neuron sends forward through. So this is what comes to the input, and this is what it fires. I probably won't go into each of the iterations, but just for you to see how things change. So this is E total is the error total, is how much we are far from the ground truth. So what we actually would like to have is this 0.1 here, so 0 on this output and 1 on this layer, on this neuron. So imagine if we have a dog picture, and this neuron is responsible for a dog class. So what we essentially would like this neural network to do is to say that this is a dog. So by giving a huge output from this neuron, this neural network will tell us that this is a dog. But essentially, after the first iteration, what we do have here is 2 outputs. Yeah, so the first output would be 0.75. So with 0.75 weight, it will say that this is a cat. And then with 0.77, it would tell us that this is a dog. So it's slightly more confident that this input image is a dog, but we are not interested in this small difference. We actually want to learn this kind of things. So what we do, we actually go back to the weights that were responsible for this output. So for these 2 computations to happen, we would like to go back to those weights, change them, so that now the output would be different. So the output would be similar to this 0.01 and 0.99. So how we do it, we basically find the gradient. So we compute derivatives and find the gradient that will tell us in which kind of way we should change those weights so that the output would be as what we want to see. So that the output would be 0.99 and 0.1. That's the way how it calculated. So basically you would have to go through derivatives at each step of the calculation of the algorithm. We would probably skip this. This is the way how it works. But essentially, the next iteration would come up with this kind of error. So this was, before we actually calculated, this was how far we were from the desirable outcome. And now, after the first iteration of the algorithm, we were slightly closer to desired outcome than we were before. And after 10,000 operations, we're absolutely close to the desired outcome. So that's approximately the way how it works. Would be, of course, better if we would go through all the derivatives, but I pretty much assume that you would die and he would die, everyone would die. That's not the goal. So deep neural networks were difficult to train back then when Hinton and other guys published those papers because they were overfitting, pretty largely overfitting, because the capacity of those networks was really huge comparing to the difficulty of the data that they had at the time. It's the high-dimensional landscapes were very difficult to train upon. Then they had the problem of vanishing gradients of the sigmoid function. Sigmoid function at the ends, it has this problem that if you take a derivative, it would be almost zero, which would mean that your other computations that would go forward would be just lost for the pupil. You would never see what was going on there. And then you have a huge dimensionality of your data and your networks, and that was pretty hard to compute. So the main problem is that they didn't have the nice big data for the analysis, and the other problem is they didn't have enough hardware to train. So first of all, no data. Deep learning, as you probably know, requires a lot of images, a lot of examples. The other thing is that they didn't have a nice and good, powerful computers to build this kind of systems on. So they were really slow at that time. So we have to study algorithms. So these are a couple of cutting-edge examples, algorithms that were developed in order to make this easier and simpler. So there is this pre-training. So before actually training the neural networks, before making this connectivity, we would like to actually train it not randomly, but give it some kind of meaningful weight so it would compute all these functions faster. Then we would have more efficient algorithms that would search for optimum faster than that was done before. And then they have developed different activation functions, which doesn't have this vanishing gradient problem, or almost doesn't have it. And this dropout, so this, remember I said about 50% lost communication in neurons. Now it's actually has been implemented in the neural networks. It has been implemented a long time back, but so now we actually use this property inside artificial neurons. So we try to mimic what our brain does in the artificial networks. Who knows why this is happening? Why do we need this dropout?
To avoid overfitting, we remove some nodes when we back forward. When we move in their back, we remove some weight. We do not touch them, so our model will generalize.
So it's a regularization, yes. Yeah. So basically, you punish your model. You try to make your model be more general. Try to make this model kind of train harder and basically not overfit your data. And this is actually neurons that you knock out. They're absolutely random. You don't know them beforehand. You just randomly kick any half of the neurons in the network. And you also need to incorporate domain prior knowledge. So still this trick is still there. So now that we are deep, we have, instead of handcrafted features, we have learned features that the representations that we actually can build based on the data. We have more representational power, and more approximation of the function that was generating this data. So this is an example of ImageNet. This is actually about ImageNet data set that they have collected this. So there is this lady, Fei Li. She is the head of the Stanford Computer Vision Lab. When I was in ICML in New York, she gave a plenary talk. And her plenary talks, mostly and TED Talks that she gave, is basically about how she collected ImageNet dataset. So she started her story about her being in the PhD studies and having lots of problems with data sets that they haven't had any data to train their models on. And she said that they were basically walking in the streets and making pictures of some cars and bushes and things like that, and buildings, just to have a data set to train their models on. But then they decided that this is not the way they want to live their lives, and they basically come up with a huge collaborative project that would collect many. So basically, then the internet would come in, and they would start having lots of images, but those images wouldn't be labeled. So they decided to organize many people around the world just to label those images, just to say what is in those images. And that was a huge collective effort that they have collected many images, and now we have this amazing ImageNet competition, and we are capable of training cool networks that would then go and distinguish between different emotions. Then we would have this phone app that you would make a picture of something, and that it would tell you that this is a chair, this is a man, this is a couple of people sitting in the room, and things like that. So what was important is that before this deep learning revolution, they had this in 2012, when the first neural network, deep neural network was trained on the competition. They had a jump from the error of 25% to error to 15%. Before that, each and new year, the increment was about 1% or 0.5% every year. So that's how much the technology has leaped the gap between the previous technology and the new technology. So in this year, 2016, the error is 3%. And how deep is the network?
150 layers.
150 layers. Huge, really huge. And you can see this is the network that was used in 2012. And now it has 150 layers of hidden unions. So the initial layer of this network captures simple features of the image. Some kind of edges, some lines, and very simple textures, but something very, very simple. Then on the second layer, you can actually see some more complicated patterns like circles, some parallel lines, some textures, and so on. And then you go further and deeper, and you see more complicated patterns that these filters can capture and then fire when they see this feature. So basically, you would this is a filter and this is an image. So you can see this how the neurons are organized in the third layer of the neural network. So you can see that filter, if you would align it with the image, it would fire a huge signal to the output layer saying that I see something. I see something that I know I saw before, and this might be this thing. So that would help us to recognize some kind of grids and some small objects and so on. And here you can even see the faces of dogs and some, I think there were human faces, not here, but truck wheels and some kind of really complicated structures that the neural network learns and then could use as a base for classification. This is just a nice, funny example just to wake you up there. So these are false positive examples saying that network task was to say if this is the same person or not the same person. So false positive meant that these were not same person, but neural network said that they were. And if you actually, you can see that they look quite similar. I mean, I wouldn't be able to say that these are completely different people, actually, myself, and maybe this too. So, and this is false negative examples. So this is when neural networks said that they weren't the same people, but in fact they were. So there was this my favorite example here. Girls do amazing stuff with their hair. So I would ever say that this is the same person, but in fact it is. Then you have, so the purpose is to say that we have different types of data, but we can actually output, well, kind of similar things, like we would name the picture, we would try to synthesize the voice, or we would just try to synthesize what was said in this audio track. Then we would try to translate from one language to the other language. One of the applications is just by looking at the chemical, say if this is toxic chemical or not toxic chemical. And what was interesting application was, can we run a code just based on the image? Can neural network run code just based on some kind of piece of or snippet of code? Or there were a couple of networks that were capable of writing their own codes. Not their own codes, but to just write the code that they have seen, similar code. Yeah, so this is an automatic annotation of images. You have a picture, and then what is in this picture? Can you describe what is in those pictures? And neural networks now are capable of doing this, so you can see a man in a black shirt is playing guitar, or a construction worker in orange safety vest is working on the road. And this is not all. Actually, now currently, this is actually solved by now. But current problem is that you have an image, then you have a textual question, and then what is the textual question is about the image. So if I would make a picture of you sitting here, I would ask some kind of questions. How many ladies sit in this room? Or how many guys sit in this room? How many people are in white shirt? And things like that. And the network has to come up with the answer. And yeah, actually it says 2 all the time. 2. Doesn't matter what you ask. Actually, only numerical questions have to answer 2, but the others have some more interesting answers. So the important problem is that we now face, and I myself have this problem, is that now, as we have a hammer in our hands, everything looks like a nail. So now the problem is that everyone tries to solve everything with the deep learning. But there are actually certain classes of problems that you should try to solve with the deep learning, and those problems have essentially some kind of nature of being hierarchically structured. So you can actually see some kind of structure in the problem which you would go and try to solve with the deep learning. And you also need to have enough data. So in bioinformatics, this is not usually the case that you have that much data unless you talk about genome. So the genome is pretty huge, it's 3.6 billion letters, but the other problem is that what to do with this deep learning in genome studies. So they actually came up with this, but this is this problem. So now we're all trying to come up with a problem statement so that you could use deep learning in there and publish in Nature and have all this kind of talks and things like that. So why it learns at all? The question is that, basically there was some kind of bunch of math, but what they have proved is that even local optima in this extremely highly dimensional problems as neural networks, because if you would imagine this 150 layer network, and each of the weight in this network is one dimension, then you could think about this kind of huge dimensionalities, and this kind of huge dimensional landscapes. Even if you would find a nice local optima, it turns out that it's a good approximation for a global optima in the whole landscape. So that's the goal. That's the message from here. And now this part with the Feynman dictum is that what you can't build, you don't understand. So what we have discussed so far was that there were many different nice inventions in the human history, and the deep learning is probably one of the next ones that we will be talking about as a great invention. And there was this summer vision project, very ambitious summer vision project by Stanford University that says that the summer vision project is an attempt to use our summer workers effectively and construct a significant part of visual system, and the final goal would be name objects by matching them with the vocabulary of known objects. So you would name the object and would say which image it corresponds to. So that summer vision project was published in 1966. Obviously, they didn't come up with anything, but at that time it was really ambitious summer project in artificial intelligence group by actually Massachusetts Institute, MIT, sorry. So just to wrap up, we have a brain that learns to see objects very similar way the neural network does. So if you would put the needle here at this part, you would actually see that neurons react to very simple features. If you would show some kind of lines or edges, they would show some kind of signal. Back here in the deep ear, the neurons would react to complicated objects like ball or some chairs and stuff like that, something more complicated. And that kind of corresponds to what we have seen in the neural network. So this is a part of the research in the neuroscience lab in University of Tartu. They try to map how neural networks train to the way we see the world with our brains. Here is this experiment that I wanted to talk about. So they have patients that suffer from epilepsy in France. The thing is, to cure epilepsy, they have to implant long electrodes inside their brain. So these are actually electrodes that go through the brain, and people are living with this kind of things. They wait for the epilepsy session. When the epilepsy session happens, they could detect the exact place of this epilepsy. And then they would cut out a small piece of brain from this place, and that would basically that would stop epilepsy. Because there was a problem in this part of the brain that would cause this kind of bug and restart of the system. But our neuroscientists, they work together, they collaborate with this university, and what they do, they show this patients images, different images of cats, dogs, chairs, and so on and so forth. What they do then is they record the signal from those electrodes. And then, yeah, so that's it. They try to map the way how these patients react to those images in their brains to the way deep learning works, to the way convolutional neural network learn those images. So they try to map. They try to build a map of the representation of the way how patients learn to the representation of the neural network. So they try to find a correlation between those two and try to prove that there is actually a good background of saying that neural networks works similar way to the brain. This is a small kind of part about the current neural networks. This is a separate type of neural networks that can memorize some of the input in order to use it later on in the output. And one of the examples was the neural network capable of writing similar texts, something that I said before about code. So this neural network has written Shakespeare-style code, Shakespeare-style text. And the question here is if you can recognize which one of this text was written by the Shakespeare and which one was written by the neural network. Can you tell me which one, the left or the right one, was written by the network? Yeah, it's probably not that easy to see. So this one is generated by whom? By the Shakespeare.py or?
Network.
This is by network.
Yes.
No, it's not because actors is randomized.
Sorry?
Or not.
No, they aren't randomized. Trust me, I have. That's my text.
The left side from Shakespeare.
The left side is from Shakespeare.
We have no idea.
You have no idea. Okay, so who has idea? What do you think? Left or right?
Well, the authorship of Shakespeare is disputed, so probably none of these texts is written by Shakespeare.
Okay, okay.
Grammar rules. What ancient grammar rules? Left side.
Of the left side. So left side is Shakespeare, the right is the machine. Okay, who thinks the left side is Shakespeare? Left side is Shakespeare, sorry. Who thinks it's the right side is Shakespeare? Both are Shakespeare's. No? No, okay. So this is actually generated by the neural network. And this is a real text. So this is actually, if you would study some kind of English literature of this centuries, you were absolutely right. So the grammar rules and things like that, you would recognize that. So this is actually a Linux text. Linux code that was written by the neural network. Yeah, I'm talking for a lot of hours today. What is amazing here is that you can actually see that brackets close and open at nice right locations where they should be. And you can actually see brackets, and then you have semicolons, and then you have equal signs, and else and if, and this is so cool. I mean, imagine then this network writing its own code and rewriting and then improving and rewriting again.
Is it compiled? No.
No, it's not compilable. No, it's not. But
If it was Python, it will be.
yeah, I mean, I don't know. But this is a bit creepy. So the Atari agent, I have a little bit touched upon the Atari when I talked about AlphaCo. It was made by DeepMind, which is the company that is standing behind this Atari playing agents. So Atari is ancient games. Who have played Atari games? Do you know if you played Atari Breakout or something like that? So these are a couple of examples of those games. Breakout. And some of them, maybe some of you know this Pong. Probably you know the Pong thing. It's very, very popular. You have these two plates that are going one against another and try to get the ball through. So what is cool here is that you can build a convolutional network that would probably take this image as an input, and then you would ask this. What the thing is that you would ask this convolution network to predict one of the three classes: to stand still, to move left, and to move right. And then you would come up with some kind of reward function that would says, if you guess it right, I give you candy. If you didn't guess right, I wouldn't give you candy. So it would try to maximize number of candies it collects. And the other thing, which is also important, it has to increase the score and not lose the lives. So this is a breakout. So this is how it plays. So actually it's pretty dumb first, and then it then it understands the point and it starts playing quite well. Actually you see it has lost only one life here, not two lives. But then it goes through this path here and it knows how to increase score dramatically. So that's the way it works. You just give it an input, and then you basically try to predict what are the control what are the instructions you would like to do. That's the network architecture that they used for this agent. So that's how it was implemented. You have input layer, and then you have output layer. Here you have two convolution layers, and then you have one hidden layer. Very simple. I would upload the slides later on, so you would. The problem is if you imagine this kind of agent playing 3D games, like I don't know, Call of Duty or some other shooter, and then what would be the difference just to deploy this model into one of the drones and let it play in the war zone or something like that? Just think about this a little bit. It's a kind of one of the issues that they have discussing now in the law making procedures, how to not let computers shoot people in the war zone. So what are the take-home messages is the brain, the first take-home message is that the brain actually incorporates and tries to make decisions for you, taking into account your prior knowledge about the world. So basically it tells you what you see by knowing what you have seen before. Then there is a kind of an overlap and similarity between how brain learns and the way how neural network learns. And but this overlap is not 100%. So there are a couple of differences, but we're still in progress in discovering how actually similar and how actually far away they are from each other. So deep learning is actually a neural network with more than 200 layers, and essentially is a neural network of next generation. So what actually is the thing, you would like to get a function that would cook from your raw data something that you can then use and get some useful results from, right? So that's the approximation of this kind of things. Neural networks and deep learning is actually pushing artificial intelligence, pushing our technology towards new and unseen heights, new and unseen technologies. And yeah, it seems like what I have told you about the neuroscience lab experiment is that this the deep learning could be a nice tool for studying how the way how we process images in our head. So by just studying the way those patients with epilepsy see images, then would bring us to some more interesting technologies. We would maybe be able to come up with an artificial sight. So have you heard of this kind of things, that there is this artificial sight idea that you could basically have a camera, and that camera would be attached to your brain, and then you would see with the camera. So that this guy was talking about it, the master hackers or something like that, the company in London. So, and comparing neural networks to the brain is almost the same as comparing planes to the birds. So birds are this biological creature that has been created by millions of years of evolution, and planes have emerged not that long ago compared to the bird's evolution, right? But we are still seeing some similarities, and we can learn from them. So these are some number of tools, but that's definitely not what I need to say here, because you guys had a lot of courses on that, and you probably know that. I would probably wrap up and stay here and probably go back to home messages. And I would say thank you very much for being here, and I would like to hear some questions if you do have them. If you don't, then I would set you free and let you go. Thank you very much. Any questions? No candy stove. Anyway. Yeah, that's social. Yeah.
Question. What's minimum viable product? What can be done with an average programmer without deep knowledge of neural network, but with some experience of programming? For example, Java.
This link somewhere here. The thing is that you could, in 10 lines of Python code, write a neural network, which would be able to. Sorry, that was a long time back, but in principle would be able to do this kind of thing. I have done it myself on data science. I had a workshop on data science, and there were participants which have filled in their motivation for the data science workshop. So I tried to play around, and I built a neural network that would take actually Russian text or Ukrainian text translated to Russian, because I couldn't find the libraries for Ukrainian text. So I should have worked with Russian text. So I have actually trained the network to write a similar text to what my participants have written in their motivation forms. So I had this nice time reading this kind of crap.
Okay.
No, it was completely crap, because when it has overfitted, it started to write nice sentences, but they were just copy-pasted from the input text. Because I didn't have that many participants, and they didn't write that much text. So it has overfitted text really fast. But essentially, what I'm saying is that there are so many tutorials that do not need any any prior knowledge in deep learning that you could just take and deploy and start working with this. It's getting more and more accessible nowadays. Any other questions? I saw another hand somewhere there. Yeah,
It's just about image recognition and how it actually works. So if I were to take an actual picture that is, 500 megabytes, and so it's a very large image, do you process every single pixel? Like, how do you actually? So you have a set of input nodes. What does that actually look like? If I were to
so the set of input nodes is actually each and every pixel of the image.
Okay, so
if you compress this, you lose information, definitely.
Okay.
And there is actually a guy in front of you who is actually teaching this course. Yeah, but essentially, yes. So the problem is most of the kind of applications is that we have to. The problem why these neural networks are not used on the devices that are in our pockets is that it is kind of it's a huge data structure. When you train this on the large images, it consumes a lot of memory, and you have to have this memory. And on device, you don't have this memory, and that's the problem. If you train it on larger images, this whole structure takes even more memory because you train it in batches and you have to store all the images and things like that and wait. So that is kind of that's a problem. But when you compress them, you lose information.
Yeah.
So on one hand, you have accuracy. On the other side, you have speed and resources. Any other questions? There was another hand somewhere here. No?
How do you think when all this deep learning hype goes to the end?
I don't know. I actually thought it should have gone through till the end already now, but it seemed to kind of. The thing is, on ICML, what we saw last year and what we have seen here this year, sorry, not here, but in New York. But the thing is that last year people were coming up with the great new ideas. I did this groundbreaking research, and now neural network can do this. This year, what we saw was that I did this small improvement from last year, and now it works 5% better. Yeah, and I took another data set from MIST or some other data set that is public up there. Now I see that my network is 1% or 2% more accurate, or it goes faster, or it learns more efficient, or something like that. So it goes to improvement now. And comparing to last year, it was more like a breakthrough, and yay, we can do now cool stuff which we couldn't do before. But now it's just like, oh, let's do one more step.
I see this paper, I didn't read it yet, from Microsoft Research. Do deep convolutional nets really need to be deep? No.
Interesting.
And they start, thinking in backward direction.
But from the other hand, on ICML, there was this residual network research that says, now deep networks even more deep. This 150 layers, that's not the end. They have made it, I think, 200 and so on.
No, 1,000.
1,000! You're kidding me. Yeah, so you see, on one hand, you're saying why they should be so deep. On the other hand, 1,000 layers. Thanks for that. So, any other questions? Then thank you very much, and let's have private questions because you still have questions. Thank you very much.
Thank you, Dmitro. I just want to add that Dmitro didn't mention another important point from his lecture, from his talk, that we should remember is 50 to 70,000 neurons die every day inside us. And if you calculate it for 1 year and 4 months, it means from 27 million to 38 million neurons. That means you should spend this time very efficiently. For example, studying at our master program here. Deep learning in deep learning program, I think, is very important, and I encourage you to take part in this program. And to also, Dmitro didn't mention that we can recover some neurons by coffee. So, and second part of our meeting is coffee, because we have coffee and data science we had, and coffee is outside, so enjoy. Thank you.
Another thing is that you can go and contribute to Yelena's project and treat Alzheimer's.
Yeah. Thank you very much.
Thank you.
funny.